So this is a picture of the distribution of the photoreceptors in the retina. So this is a picture of the back of the retina, kind of looking through the pupil of the eye, and you can see all of these little dots represent the photoreceptors position in the retina. And rods are a lot more abundant. They provide us with a kind of like a black and white vision in dim light, also in bright light, of course, too. But they're good. They work well with in a dim light and bright light. And cones work only in bright light, and there's going to be red, green, and blue cones, and they're kind of like situated closer to the center of the. So this is going to be like the macula of the eye, of the retina. So it's going to have more in the center. We're going to have the photoreceptors. Sometimes people are born with the 1, 2, or even 3 types of cones, either missing or not working function properly, and this gives people the inability to see colors, also known as color blindness or color deficiency. So it's a either absent ability or reduced ability to distinguish between colors. So this is kind of what the world would look like to a person with color deficiency. So all of these bright colors would look kind of like in the same, look kind of like one color. And this is the most common type of color deficiency called red and green deficiency. So this is the deficiency of the red cones in the retina. And so the red color is absent. So the color deficiency is more common in men. About 8% or 1 in every 12 males have the color deficiency. And here's some examples of different types of color blindness. So this is the normal vision. A person is able to see red, green, and blue colors, including yellow. Yellow is the close color to green. Because it's made by the green is made by mixing yellow and blue. That's going to be green. So green is going to be if a person can see green, they can see yellow. So the most common color deficiency is red-green deficiency. So it's the absence of the red cones. So the person is able to see greens, yellows, and blues only. The blue-green color deficiency is the absence of the blue and green photoreceptors. So only red ones are present. Oh no, sorry, this is the absence of the blue photoreceptors. Only the red and green ones are present. So actually the ability to see yellow is reduced as well as blue. And a total color blindness is very rare. So this is like when all of the photoreceptors of color, the cones, are absent. So here's a picture showing how the optic nerve is connected to the brain from the back of each eyeball. This is where the optic nerve is located. It's going to be a little bit more medial to the midline of the eye and also inferior, like we saw in the previous picture if you're looking at the eye from the side. So each of these nerves enters the hypothalamus of the brain first, but before it enters the hypothalamus of the brain, each optic nerve fibers, they do what is called a crossover, known as the optic chiasm, so they kind of switch sides. So most of the fibers from the right eye go to the left, and fibers from the left eye go to the right. So actually, the right eyeball is mostly connected to the left hemisphere of the brain, and the left eyeball is mostly connected to the right hemisphere of the brain. The optic nerves cross over in the optic chiasm, then they become optic tracts inside of the brain, and eventually end up in the occipital lobe of the cerebral cortex in the area known as the visual cortex.